Good day, Miss Uy and fellow CalEng 3 classmates. Together with Joanna David and Andrew Espanola, we are going to present the pursuit curve. In this presentation, we are going to discuss what is a pursuit curve, the sample uses of a pursuit curve, and problem solving with the use of the pursuit curve. So firstly, let us discuss what is a pursuit curve. The history of the pursuit curve traces its roots back to 1732 by French scientist Pierre Bruguière. However, it was formally coined by George Boole a bit later on in 1859 in his work titled Treatise on Differential Equations. By definition, the idea of a pursuit curve is that a point, which we will call the rabbit, follows a prescribed curve. The rabbit is followed by another point, which we will call the fox. Two conditions will be specified to determine a pursuit curve. First, the fox heads directly towards the rabbit, and second, the fox's speed is directly proportional to the rabbit. However, you might ask, why is this a pursuit curve or differential equation? It is because two or more functions are related to it with regard to its rate. In this case, the two will be the one chasing and the one being chased. In a real life scenario, it would be analogous to a thief and the police, wherein the fox is the police and the rabbit is the thief. In the graph presentations you can see now, we can say that black is the thief and red is the police chasing the thief. Today is it is widely used in fields such as military and law enforcement, in fields of military in terms of fighter aircraft and the like.
The trajectory path of the cup is defined initially by this equation, wherein u is the constant velocity of the thief, while v is the constant velocity of the cup. So simplifying, we would be getting negative x y double prime. So from the given equation before, we just need to multiply it or both sides by negative v over u to be able to come up with this equation, wherein k is equal to v over u greater than 1. So let us remember this because we will be needing this equation until the end of this derivation. So to get the differential equation, we just need to let w be equal to y prime. So we will be coming up with this equation wherein y prime is also equal to dw over dx. Also, as we could observe in this equation, variables w and x could be separated. And then applying the method of variable separable that we have learned from the CalEng 3 class, the equation will now be like this. So integrating both sides, we would be coming up with arc sine hw is equal to 1 over k ln x plus ln c. And then we need to substitute x to L meters because it is the initial distance between the cup and the thief, and then we will be equating it to 0. So applying the rules in natural logarithmic equations, hence c will be equal to e raised to negative 1 over k ln L. And then going back to the equation earlier, substituting c, we would be getting this. And then simplifying, we would be getting arc sine hw be equal to 1 over k ln x over L. Remembering the definition of hyperbolic in sine h, it is equal to ex minus e raised to negative x all over 2. So now we will be solving for w, which is also equal to dy over dx. It is this. We will be getting this equation. And then, as I have said earlier, we will be using the hyperbolic in sine h. And then solving for w, we just need to integrate this equation. We will be getting this. So based from the initial condition that we used earlier, x is equal to L and y is equal to c, we will be solving the value of c. So we will be getting lk all over k squared minus 1. Substituting c to the equation that we have earlier, which is the final equation of the trajectory here. we would be getting this. For us to know the time that the cup took to catch the thief, so from the equation that we have derived a while ago, which is the trajectory path of the cup, we need to make x is equal to 0. So this equation will be cancelled. So y will be lk all over k squared minus 1. So from the initial condition that I have said to you that we need to remember, which is the k is equal to v over u, we just need to substitute it to this equation, and then we will be getting this. Simplifying, we will be getting this equation, and then y is equal to L uv all over v squared minus u squared. So remembering the formula of the distance, which is equal to velocity times the time, we will be using that. Thus, the formula of the time required to complete a successful chase, or simply for the cup to catch the thief, would be t is equal to L times v all over v squared minus u squared. So this.
So for the next part, for the sample problem, a robbery incident happened in front of De La Salle University Manila campus. Student who witnessed the incident immediately called out for help, and shortly, cops from Manila police arrived. The cops began to think of ways on how to chase the thief as soon as possible, and so they decided to ask help from the silent engineers to calculate the minimum time it requires for the thief to be chased. The engineer noticed that the path wherein the thief takes follow a pursuit curve or trajectory which is 100 meters away from him. The thief runs and has a constant velocity u of 5 meters per second, while the cup has a constant velocity v of 8 meters per second. Suppose you are the engineer. You need to calculate the minimum time required for the cup to successfully chase the thief so that the thief will not be able to escape. So for the solution part, we first write the given, and we have the distance L is equal to 100 meters, the thief's velocity u is equal to 5 meters per second, cup's velocity v is equal to 8 meters per second. And since the path the thief takes follow a pursuit curve or trajectory, we will use the differential equation derived previously using the variable separable method, which is t is equal to L multiplied by v all over v squared minus u squared. And by substituting the given to the formula using the variable separable method, we will have the 100 meters multiplied by 8 meters per second all over 8 meters per second squared minus 5 meters per second squared. And we will obtain a value of t which is equivalent to 28.57 seconds. And therefore, the minimum time required for the cups to successfully chase the thief so that the thief will not be able to escape is 28.57 seconds. So in here, we will see how important differential equation is into real-life situation. Also, we have been able to utilize the lessons we learned from this course, such as the variable separable method in deriving differential equation in order to solve engineering problems, particularly in the concept of pursuit curve or trajectory. So that's it, and thank you for watching.